else here.
Perfect.
Yes.
So in that case, maybe just a brief introduction. So it's my pleasure to introduce this week's speaker in the latest edition of the MetaMAT seminar series. Today we have Malte Röntgen, who's a postdoc from the University of Hamburg. He works in the Center for Optical Quantum Technologies. And today he's going to talk to us about latent symmetries. So Malte, over to you.
Yes. Thank you, Bryn, for the very nice introduction. Thanks, Bogdan, and the other organizers for this invitation. And thanks to all the participants here for being here and listening to my talk. So the topic is latent symmetries, and I guess that by far most of you have never heard about this topic. So let me start by giving you, or let's start by something which we all have common ground with. And this is, of course, the concept of symmetries. And as we all know, symmetries are really of overwhelming importance in all areas of physics. Symmetries guide the fundamental form of physical laws. They allow us to make statements on degeneracies and also to derive selection rules. And what is very important to me is that symmetries allow us to make predictions without solving the underlying equations of motion. And this brings me to the next slide. What we can see here is on the left-hand side is a very simple four-side tight banding model. It's very simplistic. And what you should immediately see is that it has an obvious reflection symmetry along this axis here. Now, due to this reflection symmetry, without solving the underlying four-side matrix Hamiltonian or 4x4 matrix Hamiltonian, you will immediately see or know that all the eigenvectors will have parity on those two sides U and V. This is now very basic and one might say even trivial. So let's get to non-trivial stuff now. On the right-hand side, you can see a system which has a latent symmetry. And I'm going to tell you in a second what this means. But for now, let us just start by inspecting this system. It has 9 sides, so it's described by a 9x9 matrix Hamiltonian. Very simple, tight binding. But what is important here is that it has no symmetries, in the sense of there's no reflection or inversion or rotation, which leaves this 9-side system invariant. So in other words, if you would look at it or inspect it, you would just say, well, it's obviously an asymmetric setup. And from such an asymmetric setup, we do not expect any specific properties on the eigenvectors. Yet, if you do this, well, type down this Hamiltonian in Mathematica or MATLAB or your ever favorite computational algebra machinery, you will find that all the eigenvectors have parity on those two wet sides U and V. Now, the big question is, where does this parity come from? Is it something like accidental, or is there something more behind it? And of course, if I ask like this, there is something more. And in order to understand where it comes from, let us first go from this full Hamiltonian picture to an effective Hamiltonian. By effective Hamiltonian, I mean that we go to a specific one, namely the one obtained by subsystem partitioning. And in order to do this, we would need first to partition our system into subsystems. In this case, we choose 2 subsystems. One subsystem S, consisting of the 2 wet sides U and V, on which we have parity. We call this set S. And then we need the complement, so all the other sides, which is just the gray stuff here. Now we have partitioned our system. We can write down our Hamiltonian in block form like this, with, for example, this 2x2 matrix HSS, describing just the isolated subsystem consisting of the sides U and V. So now for the formality, we can go to mathematics. So we have the underlying eigenvalue equation. So our matrix times our eigenvector is energy eigenvalue times eigenvector. And if we write it down in block form like with this structure here, what we get are 2 equations. One for the eigenvector components, the subsystem S, so YS, and one, so complement, so to say, for the eigenvector components on S bar. Now we want to get rid of this annoying S bar stuff because the parity exists only on S. So what we can do is we can solve this second equation for YS bar and insert this resulting expression into the first one. And if we do this, we arrive at equation 1 here with this effective Hamiltonian defined here. Now this, in case you wonder, this inverse here comes from the fact that we had to well, do an inverse operation here in order to solve this second equation for YS bar. Now, if you look at this, you might say, well, what did we gain? Now we started with a very nice and simple tight binding setup, and now we arrive in this very ugly effective Hamiltonian. In order to write it down, we would have to solve this nasty inverse matrix here. And this is all true, but the real power of this approach is if we come down to the result. So if we do this operation, so this effective Hamiltonian for our system, what we will get is a B-symmetric matrix. B-symmetric, I mean that the resulting matrix here is symmetric both about the diagonal and the anti-diagonal. All the entries are energy dependent because it's an effective Hamiltonian and we had this inverse operation. But now what is important, this B-symmetry, well, it's a symmetry. And if you want, you can visualize this 2x2 matrix in a graphical form where you identify these funny looking loops with the diagonal or on-site effective on-site potentials. And now if you look at this graph here, you will immediately see that it has an obvious reflection symmetry about this axis here. And this is exactly what a latent symmetry is. A latent symmetry is nothing else but a symmetry in the effective Hamiltonian. And what is very interesting, I mean, it can be easily shown, details will not be given here though, that if you have a latent reflection symmetry of two sides, such as we have here for U and V, then this is really equivalent to the statement that all eigenstates of the underlying Hamiltonian will have local parity on those two sides. So in other words, we started from something ugly, which has some nice property, namely parity. We did this effective Hamiltonian. The system description became more complicated due to this effective, due to the fact that our system here now is energy dependent. But on the other hand, it allowed us to detect something which was otherwise hidden from our vision. Now, before I continue, let me give you some more facts on this effective Hamiltonian written here again for convenience. As it turns out, this effective Hamiltonian is also known in spectral graph theory, where it goes under the name of isospectral reduction. Now, if you wonder why do they call it isospectral, the answer is as follows. If you say for a moment that this E here is a completely free parameter and not just constrained to be the specific eigenvalues which we had before, so E is a free parameter, then you can define the eigenvalues of this effective Hamiltonian through this expression. So this is nothing else but the normal definition for eigenvalues of a matrix, though now we have replaced the normal matrix with scalar entries by this effective Hamiltonian, which has entries which are themselves dependent on this parameter E. So it's a nonlinear eigenvalue problem. And if you solve it, or let's say what you can easily show is that in the common case where your original Hamiltonian and the one constrained to the subsystem S bar, so the outside which we want to exclude through our effective Hamiltonian approach, when these two Hamiltonians have no common eigenvalues, then the eigenvalues of your effective Hamiltonian are exactly the ones of your original Hamiltonian. No eigenvalue is taken away, and no additional eigenvalue is added. And this motivates calling this effective Hamiltonian the isospectral reduction. Now, in this remainder of this talk, I will most of the time, unless I forget it, denote this guy here by the isospectral reduction and not by the term effective Hamiltonian. And this is partly done by me in order to acknowledge that latent symmetries, interestingly, have not been first found in physics, but in graph theory. And in fact, it was very recent. This paper here is from 2019. And for me, that was a really breakthrough, or let's say not breakthrough, but a very interesting point in my PhD. I was working at that time on local symmetries, so symmetries which are present just in a part of the system. And I was looking for new literature, and then I stumbled upon this paper, and this really opened my viewpoint towards graph theory. And we will see a couple of examples in this talk where it becomes obvious then that if you look in the literature for spectral or normal graph theory, you can really learn a lot. Okay, now back to physics, away from graph theory. What I have shown you so far was a little of a very simplistic and maybe even trivial tight binding model. Now, the underlying theory of latent symmetries, however, is applicable to a broad range of physical setups. All what we need is this matrix eigenvalue problem shown here. And I have to emphasize this matrix H, it could even be a non-Hermitian matrix. As long as it's diagonalizable, we can apply the concept of latent symmetries on this particular system. Now, just to give you some examples on which we have also been working on, of course, this eigenvalue problem here includes tight binding models, but it can also be applied to the problem when you have light propagation in evanescently coupled optical waveguides, where, for example, each waveguide has just one fundamental mode, and then if you place these waveguides together and apart from each other in the order of a few microns, then these fundamental modes overlap and you get some coupling, and at the end you can describe it by pretty much this equation here. So you can find latent symmetries in these setups as well. Also, if you replace your Hamiltonian here by the S matrix, the scattering matrix, you can also define latent symmetries in a multiport scattering setup. Then this is something which I will talk in the end of this seminar today. We can also find latent symmetries in eigenmodes of coupled acoustic waveguides in the low frequency approximation. Also for normal modes of spring mass systems. And last but not least, I could not resist. You could in principle, and we have even found it but not published yet, find latent symmetries even in discrete many-body Hamiltonians. So the way to go there is to start from a second quantized Hamiltonian operator, go to a specific basis, let's say by taking the basis of number states, then you get a Hamiltonian matrix. This might be very huge though, but in principle, you arrive at this matrix eigenvalue problem above and can find latent symmetries in many-body Hamiltonians. Now you might say, talk is cheap, show us some physics. So let us, before going more into theory, let us just look at one particularly simple example setup, namely a one-dimensional spring mass setup. And before we start with latent symmetries, let us just investigate those systems for the case that we have a normal reflection symmetry. So what you see here is a very simple setup. We have 4 blocks or 4 masses. All of them have the same weight, so same mass, and they are connected by springs with different spring constants, given here. The first and the last are connected to a fixed wall. This resembled by those black structures here. And now what we're interested in, well, we want to convert the physics of this system to something which we can treat by the concept of latent symmetries. So we need a matrix eigenvalue problem. And then, I mean, most of us have, or I think all of us have done this in the studies. We look at the normal modes. So we solve Newton's equations, the equations of motion, say that we have harmonic excitations of our individual masses. And that what we arrive is this nice equation here, where we have V is a stiffness matrix, X is the eigenvector, it's an eigenvector of V corresponding to a normal mode. And the entries of this vector are the amplitudes. So for a normal mode, all masses oscillate with the same frequency omega. And the individual amplitudes are given by the corresponding entry of this, in this case, 4-dimensional vector. Now, of course, in this very simple setup, we have, well, U is a very simple interaction potential. And the V matrix or stiffness matrix, you can derive from U just by taking the second derivatives. You can also call this guy here the Hessian matrix. And if you do this due to the reflection symmetry, oh, I forgot, I was too fast. Now, to get things more pictorial, let's do this. I mean, write down this stiffness or Hessian matrix for this particular setup. What you can see is, well, we have some on-site potentials or diagonal elements. These come just for each mass. They are the sum of the attached spring constants. So for mass 1 is connected to 2 springs, with 2 springs, one of constant k prime and the other one k double prime. and this appears here in the diagonal, and the off diagonal are just the corresponding couplings between the masses I and j, and there's a minus sign in front of it. If you pictorially depict it as a graph, as I will do in this talk many times, well, we have the game, this game of identifying these diagonal elements with loops. I will explain in a few slides why we always do this. And then, of course, the normal lines, yeah, just the corresponding off-diagonal elements. Now, again, no matter whether you look at this picture above here or below, you have this obvious reflection symmetry. And as a result, you can immediately say that the eigen or the normal modes will have parity. In particular here, for any normal mode, the sites on masses 2 and 3 will have parity, and the masses 1 and 4 will have parity. That's why I colored them. Okay, so far so good. This is all kindergarten. And now let's go to latently symmetric spring mass system. So what I have done here above is, again, a 4-mass system. But now if you note the difference, the spring constants are a little different. And indeed, they are really fine-tuned such that we will have latent symmetry. And how exactly we get to it, I will explain now. So if we play the same game, I mean, deriving the equations for the stiffness matrix, we can write it down. It looks like this. What is important now is that even here now you don't see any particular symmetries. This matrix is not bisymmetric, and the corresponding graph has no reflection symmetry. However, if you then do this isospectral reduction over those two innocently looking masses 1 and 3, you will get this expression. So a 2x2 matrix. It is lambda dependent. So lambda was our eigenvalue, m times omega square. And well, the exact structure I don't really care about. What I care about is that these two elements, this diagonal and this diagonal here, are the same. So it has this structure, it's bisymmetric, or drawn as a graph now, it has an obvious reflection symmetry. Now this reflection symmetry in our isospectral reduction, if we think back to what I told you some slides ago, means that these masses 1 and 3, over which we reduced, are latently reflection symmetric, which from all these chains of statements which I gave you means that all eigenmodes or normal modes will have parity on those two sides. And now just to repeat my statement, talk is cheap, show us some results. I computed those, or let Mathematica compute the eigenmodes or normal modes, and what you see here are the 4 normal modes. And then if you look at the first and the third line, you will see that the first normal mode has positive parity, 2 and 3 have negative parity, and the fourth has positive parity as well, just as I promised. And you see that all normal modes of this very asymmetric looking system will have parity on those masses 1 and 3. Now, why did I show you this example? So first of all, I wanted to emphasize that you can really apply the concept of latent symmetries to even a very simple toy model. And second, this toy model doesn't need to be big. Yeah? It is enough to have a spring mass chain consisting of 4 masses to already get latent symmetries. Now, if you think about that, you can do this, of course, also to larger networks. Then, of course, the design will get more complicated. So in this case here, I could derive simply by computing for, let's say, if I would wanted to design these latent symmetries, I would give 1, 2, 3, 4, 5 different spring constants, leave them as free parameters, then do the isospectral reduction, which would then depend on lambda and on this 5 spring constants. And then I would try to solve this equation. So I would demand it to have this structure for all lambda. If you do this for all lambda is important because it gives us then a large number of equations which we can ultimately solve, in this case, to get relations on the individual spring constants, which at the end gave us these individual values. Now, of course, if you go to a larger system, you might say, and this is correct, it will be very difficult to find analytical expressions and probably even to find something numerical. And this was something when we started this research on latent symmetries. This was something which really bothered us, and we were desperately looking in the literature, in the graph theoretical literature, what one could do. So our aim was to derive something like a construction principle, maybe not for these spring mass systems, but for some easier setups. And yes, this brings me to the next part. So we have to go to graph theory again. And the aim of all of this is to derive some rules which we can use to build a latently symmetric setup. Now, again, what I like about graph theory, they're always fast and they're good at mathematics. And it turns out, and this was done only 2 years ago, it turns out that if you have a real symmetric Hamiltonian H, just as we had before with our stiffness matrix, the fact that two sides U and V are latently symmetric, meaning that the isospectral reduction has this nice reflection symmetry, this fact is equivalent to the statement that there's a specific relation in the matrix powers of your Hamiltonian. So what you see here is you take the kth power of your Hamiltonian, so k equal 1, 2, 3, and so on, until n minus 1, where n is the dimension of your Hamiltonian. So for the first few matrix powers, you take the kth power, and then evaluate the uth diagonal element and the vth diagonal element. If these two coincide for all k here, then this is equivalent to the statement that your isospectral reduction has this nice reflection symmetry for any value of lambda, or whatever you call your spectral parameter, E, or you name it. Yes, so let's go back. So again, you can see it's a mathematical journal where this proof was published. It's not done by us, I have to emphasize. And it's again spectral graph theorists who did it. Now to give you a little more, so to tease you a little more on spectral graph theory, there's something more that we can learn. So this is what I gave you on the previous slide. Latent symmetry is equivalent to the statement on the diagonal entries of the matrix powers. And then it turns out, also done in this 2020 paper, this connection, that this statement, equation 5, is really equivalent to, or can be related to the eigenvalue spectrum, not of the original Hamiltonian, but of some derived Hamiltonian. And to see this, let's start. This is our original Hamiltonian, which had these latently symmetric sides U and V. And then from H, we can construct two sub-Hamiltonians. H minus U, obtained from H just by removing U, and the same for H minus V, by removing this guy. Now, these two guys, they look completely different. But now the statement is, proven in graph theoretical language, is that these two very different looking systems have exactly the same eigenvalue spectrum. And they are thus called cospectral. Since H minus U and H minus V are cospectral, in graph theory language, we say that U and V are cospectral vertices. And now we can see cospectral vertices is equivalent to this statement on the matrix powers, is equivalent to the fact that our isospectral reduction or effective Hamiltonian has a reflection symmetry for all values of the spectral parameter. And what I find personally very intriguing about this, that it connects three seemingly very unconnected concepts. An effective Hamiltonian on one hand, the matrix powers on the other, and then going even further and connecting spectral properties of subsystems. And then what I find even more intriguing is that if you look at the citation down here, the concept of cospectral graphs and even of cospectral vertices has been done already in 1973 in graph theory. And as a side remark, cospectrality is something like, well, you can think of it as a similar question to, can you hear the sound of a drum, where the question was, can you have two different shaped drums which have the same eigenfrequency spectrum? And graph theorists had a similar question, and the question was, can you have two different graphs which have the same eigenvalue spectrum? And then this was not really settled until Schwenk made this very nice paper in 1973, and he showed, first of all, yes, it can be it can well be that they are co-spectral graphs. And second, if you investigate a certain fraction or a certain subclass of graphs, almost all graphs are co-spectral to each other. So this was a very groundbreaking paper in 1973 in graph theory. Now, we had a small detour learning about matrix powers, and now comes even more. And it turns out this is something which any graph theorist learns, let's say at kindergarten level, so maybe first semester of bachelor or second. For me as a physicist, it was completely new until I bothered one day to look into a basic graph theory book. And it turns out that you can connect the powers of your matrix or of your Hamiltonian to a concept called walks. So let me show you what it is here. Let's say we have your simple Hamiltonian. Any link here corresponds to a coupling strength of 1. We have this funny loop here. And then, well, the matrix element Hij, just say, well, it's a coupling strength between vertex or side I and side j, as depicted here. Now, if you square this Hamiltonian, so go to h second power, the statement is as follows. The matrix element Ij of your matrix h to the power 2 gives the number of walks starting at vertex I and ending at vertex j. And the walks have to have length 2. So let's do this now. So we have second power. We look at the matrix element 1, 1. So we have to look at walks starting at vertex 1 and ending at vertex 1. And in between, we are allowed to make 2 steps because we are looking at the second matrix power. And now we can do this. So we start at vertex 1. First of all, there's no loop attached to it. So we cannot go in a circle, so to say. And this, by the way, is the reason why graph theorists normally make this diagonal element depicted as loops. So there's no loop. So we have to go to another vertex in order to come back to vertex 1. So what can we do? We can either go to vertex 2, 1 step, and back 2 steps. And this is exactly the first walk shown here. Now we can do the same, go from vertex 1 to vertex 3 and back. This is the other, and these are all possibilities that we have. And then the usual rule is if you go, so you can play the same game here for any of those matrix elements. If you want, it's also this exact example is taken from our paper here. And if you go to the kth matrix power, it's the same principle. The matrix element h to the power kij counts the number of walks starting at vertex I, ending at vertex j, with exactly k steps. You can generalize the statement to cases where your matrix has elements not 0 and 1, but some arbitrary ones, floating point numbers. You can also make this, generalize this statement for the case that your matrix is non-Hermitian, and that can be arbitrarily complicated. But at the end, the take-home message is you can relate matrix powers, which we now have seen are important in the theory of latent symmetries. You can relate those matrix powers to the concept of walks, which, if you think about it, is somehow also connected to the concept of interference, right? If you have some wave going into a structure, you have to sum up all different paths in order to see how it propagates through the structure in order to get interference patterns. And now let's connect this concept to the concept of latent symmetry or to co-spectrality. We know that for latent symmetry of 2 sides, this equation has to hold. So diagonal elements of matrix powers have to be the same, which in particular means if we have such a simple matrix of zeros and ones only, as shown here, if 2 sides U and V are latently symmetric, they are the same number of walks going from U to U as from V to V. And in particular, since, as you can easily show, the second power, so h to the power 2, counts the number of neighbors of those sides. So for example here, side 1 has 2 neighbors, and then you see h to the power 2, 1, 1 is equal to 2. This means that a necessary condition in order to have a latent symmetry of two sides is that the two guys have the same number of neighbors. And if we go down 2 slides, here you see U has 2 neighbors and V has also 2 neighbors. So it's obviously fulfilled. So in other words, we can learn a lot, or we can derive some conditions which we can intuitively understand in terms of walks if we are to design a latently symmetric Hamiltonian or latently symmetric setup. Now, you might say, well, this is all good, but I don't want to end up in this combinatorial nightmare of computing the 90th power of my Hamiltonian and counting all possible walks of length 90. So is there some other stuff? Is there some possibility, some method which I can use in order to construct out of nothing or out of nowhere a graph or Hamiltonian with latent symmetries? And the answer is yes. Again, graph theory is our friend and helper. There are different methods. The most popular one is the so-called Gaussian-McKay switching, which can be used to construct cospectral graphs, and thus also graphs with cospectral vertices. I'm not going into details here. And what I personally use mostly, I'm a big friend of brute force approach. So I use the so-called naughty suit. It's not naughty, it's naughty. Don't know why they came up with this name. It's called not an automorphism. Yes, it's a program suite used to give labels to graphs. And what is really powerful at, it's good if you want to generate a huge number of graphs, let's say all graphs with 10 vertices, and then afterwards, let's say scan all these graphs for latently symmetric vertices, for example. And just over there's a comma different. Just to give you an example, on my really dated laptop, Naughty took just, I think it's 11.7 million graphs were generated in just about 5 seconds. So this program is really fast. So let's say you took Naughty and looked for your favorite, or you found your favorite latently symmetric system, and you might say, okay, but I want to make it bigger. I don't want to have this very small, maybe 10 or even 20 vertices. I want to extend the system while keeping the latent symmetry. And this is where our research comes into play. This is a very young paper, or recent paper from 2021. It's a pure mathematical monster. So let me give you one main point what we derived in this paper. Let's say you have this rather chemical looking latently symmetric graph. It has 2 latent symmetric points here, U and V. And now, so our aim is to somehow make this system bigger or larger without breaking latent symmetry. And what we did is we first brute force trying to connect different sites somewhere, and then we found out sometimes you can connect something without breaking latent symmetry and sometimes not, and we were not finding any pattern behind this until we took great care and said, okay, we have seen before that the diagonal elements of our matrix powers are related to latent symmetries. What about the off-diagonal elements? And then it turned out that this graph, for example, this side C here has a very specific property. U and V are the 2 latently symmetric points. And then if you evaluate the case matrix power, as always, and look at the off-diagonal element UC, you will find that it's exactly equal to the off-diagonal element VC. So the number of walks of any length from U to C is equal to the same number, the number of walks from V to C. So this side C here somehow has the same distance from those 2 sides U and V. Now we can come back to what I said earlier about interference. Let's say we excite the 2 sides U and V with amplitudes plus and minus 1. So we do an anti-symmetric excitation of those 2 sides. What will happen in time? Well, we have some time evolution operator, so e to the power iht. it will be applied on our vector. But now, since in any matrix power, well, the off-diagonal element UC is equal to VC, and since U and V are excited with negative parity, this excitation can never reach this side C. So in other words, if we do this excitation, anti-symmetric, U and V, no matter how long we wait, they will never ever be amplitude on this side C. Now, this, for example, you might use if you have a network of oscillators and you want to keep an excitation in a subnetwork. You just find the latently symmetric points and these specific sites, and then you can divide your network into subnetworks. In our work, we call these specific sites C, which fulfill this property. We call them singlets. It has nothing to do with spectroscopy, though. We just needed a fancy name, and well, they will also be multiplets. And what we also found out is if you have a singlet, well, if you have this equation here, then it can be easily shown that you can connect an arbitrarily large subsystem. This capital C here in the cloud, it can be as big as you want. You can connect it to this singlet, and no matter what you do in this cloud here, the latent symmetry in the full network will never be broken. And this means you can start from a very simple setup, start with this graph generated by this Naughty suite, identify the singlets by scanning your matrix powers. This is something which can be very efficiently be done, for example, in Mathematica. And then you can play Lego and you can make your graph as big as you want without breaking symmetries. Now, if there are singlets, you might say, and I already answered this, are there multiplets? And of course they are. So if you here, instead of using a single side C, sum, or let's say replace C by a set of sides and then sum over the expression for all of those, you will get what we call a multiplet. So this is shown here. So you M is a set of sides and you sum over the corresponding off-diagonal elements in all matrix powers. And if this sum is the same for U and for V, then the set M is what we call a multiplet. And multiplets are nice because you can use them to create singlets. So here, M1, M2, and M3 are, well, a multiplet consisting of 3 sides, so triplet. This is, by the way, the reason why we use this particular terminology. So these 3 sides form a triplet, and this means we can now, if we symmetrically connect a new side, C prime, to this triplet, the new side will become a singlet, so C prime will be a singlet, and thus we can also connect an arbitrarily large subsystem to it without breaking latent symmetry. So altogether, we have now, and this is which I cannot emphasize enough, the analysis or thorough analysis of the matrix powers allows us now to learn a lot about our systems. And I think this is something like a shifting of viewpoint, because at least I before have never used matrix powers. I worked with the Hamiltonian, maybe with the time evolution operator and the eigenvectors, of course, but I have never tried to investigate the matrix powers in more detail. Now, not sure if this is a right community though, but let me briefly show you one example of what we can use latent symmetries for. In the condensed matter community in the last years, the concept of flat bands has been really a hot topic. A flat band is really, as the name suggests, it's a band which is completely flat. There are some reasons why people are interested in those. For one, they might be connected to high temperature superconductivity. But for other reasons, just to give you one example, if you have a perfectly flat band, then the group velocity vanishes. So because the group velocity is proportional to the curvature of this band, and this band, which is flat, has obviously no curvature. So you can have very interesting phenomena. And in this community of flat bands, there's always the question of how can you generate these systems. There are many different construction principles. Some are very basic, some are more involved, and we just thought, well, we have now this multiplet principle, and we have latent symmetries. Now let's use these two concepts to derive or to create a flat band generator. And the logic is quite easy. So you start with a network with latent symmetries, and if you're interested, I can always send you a huge MATLAB file with millions of them. Otherwise, you can just generate them by yourself with that naughty suite. Then, if necessary, as a second step, we need singlets, so you can equip them by evaluating the matrix power. And then as a result, if you have singlets, you will have one or more eigenstates, each of them vanishing on all of these singlets. Yeah, each of these eigenstates has negative parity on the latently symmetric points. For example, here in this network below, I showed you several times now, U and V are latently symmetric, and these three right sides here on this line, they are singlets. So any eigenstate which has negative parity on U and V will vanish on those three. And now in order to construct a flat band, all you need to do is you take such a guy here with one or more singlets, create a lattice. It could be 1D, but it can be in arbitrary dimensions. And you connect these different unit cells exactly at the singlets. Now what you get is, of course, a periodic structure. You will get a band structure as well. And now, due to this special structure of these negative parity eigenstates, it can be easily shown that for each of those unit cells, these eigenstates are still present locally. Yeah? They are exact solutions of your full Hamiltonian, where everywhere else outside of this particular unit cell, this vector is just 0. It's exactly 0. And then, well, you will have one of these eigenstates for each of your unit cells. All of them have the same energy. You have macroscopic degeneracy. And as a result, you can superpose them for any crystal momentum k, and you will always get this flat band structure. Okay, so now let's get more into more everyday physics, so to say. And I want to talk a little bit about acoustics now. Well, and this is done partly, first of all, to show that, well, you can find latent symmetries not just in tight binding models or in these one-dimensional spring mass systems, but also in more involved structures, which nevertheless can be quite simple. So what do we have? We have this following setup shown here. It's just 3 waveguides. They have the same length, same, how do say, it's not width, this is a width, so different width, and the same height, d. And we are interested in the eigenmodes. These waveguides are formed out of steel. So if we want to know the eigenmodes of these guys, we have to solve this 3-dimensional Helmholtz equation with P being the acoustic pressure. So in other words, the deviation of pressure from the ambient pressure of 1 bar. And the boundary conditions are Neumann. So the normal derivative of P vanishes whenever we are at one of those surfaces, which are made of, let's say, steel. Now, if we want to apply the concept of latent symmetries onto this system, we have a problem at first glance because, well, we need a matrix eigenvalue problem, and this is a continuous operator. But it turns out, if we work in the limit where the waveguides are much longer than they are thick, the 3-dimensional Helmholtz equation becomes a 1-dimensional in each of the waveguides. So we have second derivative along x direction plus k square of p equals u in each of those waveguides. So they are just plane waves in them, as you can see, for example, here. This is one eigenmode picture. And then if you think about it, well, what do you have? You have a waveguide, which is 1-dimensional now, since all the length is much larger than the other dimensions. It's a 1-dimensional waveguide, 1-dimensional Helmholtz equation. It's second order, not second degree, second order differential equation. So you can reconstruct the wave field in this waveguide everywhere, as long as you know the pressure at, let's say, 2 endpoints and the wave number k. Yeah, these 3 pieces of information are enough to reconstruct the wave field everywhere. And this is what we need. So in other words, we can collapse this continuous system first into 1D and then even into 1D discrete by evaluating just the pressure at these interface of boundary points here, 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 and there. This is just the ends of the individual waveguides. And then if we go more into details, what we will get is the following discrete or generalized. It's a generalized eigenvalue problem, which is also discrete. So A and B are matrices, which I'm going to explain in a second. Cosine KL is our eigenvalue. And the P vector is the pressure of a corresponding eigenmode if you evaluate it only at those 4 boundary points 1 to 4. Yeah? As I said before, if you have the pressure at the ends of a waveguide and the wave number k hidden here, you can reconstruct the wave field everywhere. So this is somehow the logic why we can get from here to there. Now the matrices A and B are as follows. A is what I would call a topology matrix. So matrix element aig is equal to the width of a waveguide between endpoints I and j. Yeah, as you can see here, between the first 2 points, there's a waveguide with width W12, and this is exactly what you see here. So it's a tridiagonal matrix in this simple case here. B is a diagonal matrix, and B is something like, well, it's not something. The diagonal elements are just the sum of neighboring waveguide width. So B11, well, this point has just one waveguide attached to it, so it's equal to this. B22 is equal to the sum of this guy plus this guy. And then if you are familiar with generalized eigenvalue problems, well, you can do this nice transformation shown down here. Because your matrix B is positive definite, this guy here always exists. And then you will get a real symmetric matrix Hamiltonian, and you will get to a normal matrix eigenvalue problem, which I didn't wrote down here. Now, if we have a normal matrix eigenvalue problem, this is our starting point, because now we can look for latent symmetries. And it turns out, this is what I really like about this system. If you set here this width here equal to the sum of this and this width, this alone is enough to get a latent symmetry between the waveguide points 1 and 3. So between here, the point here, and the point there. Now we have to go back. So we have a latent symmetry in our Hamiltonian H. The eigenvectors, so this piece of our Hamiltonian, give the pressure of an eigenmode, I mean a continuous eigenmode, at those endpoints. So now this means that our latent symmetry of our matrix Hamiltonian corresponds to local, or I would say pointwise parity of our eigenmodes. And this is schematically shown here. This is really a solution of the continuous this operator equation. And as you can see here, the pressure at this point, really at this point, is equal to minus the pressure here. Well, up to these small 2D effects where you don't have exactly a plane wave, but this small curvature. Yeah, and now we have latent symmetries in a rather continuous system. Yes, it's somehow discretized, but it's still continuous. And this is, well, I find it quite funny and quite intriguing as well. What can we do more with it? Well, first of all, we could think, or we can investigate what happens if we deviate from this case where we have very long and very narrow waveguides, where this ratio of the maximum width over the length, which is the same for all waveguides, is equal to 0. At this point, well, what is shown here is so to say the parity of the eigenmodes. If you look at, so you compare the pressure at point 3 and point 1. These are the latently symmetric points. And we just evaluate the eigenmodes which have negative parity. In the case where we have really exactly fulfilled this limit, so W max over L is 0, we have exact negative parity. And then you can see if we deviate from this, make the individual waveguides larger and larger, you would expect normally, or I would have expected that this parity picture breaks down completely. But it's not the case in this system here. You see, even if you have very large deviations, the deviation from parity is still quite small. And by the way, in the above here, I didn't mention, I should have started with this, I think. What you can see here is just the profile along the x direction for different eigenmodes. So all of the modes have been normalized to start at 1. We have Neumann boundary conditions, so you can see the slope is 0 at this point here. Then the different eigenmodes, well, they behave differently. They're all waves, of course. And then at this point here, at point 3, they all are either +1, these are the positive parity eigenmodes, or -1, which are the negative parity eigenmodes. And again, you have some system which looks very innocent, very asymmetric at first glance, and you would not expect anything. And then you investigate the matrix powers and you see that there's a hidden symmetry or latent symmetry which induces pointwise parity in your eigenmodes. Now, all what I have shown you before with the multiplets can be applied here, though it's a little more involved because our Hamiltonian is derived from our topological matrix A and this diagonal matrix B. So this multiplet principle can be applied, but it becomes a little bit more involved. But what is immediately, or should hopefully immediately be clear, is that if we have two latently symmetric networks, such as shown here, so we have network A, where 0.1 and 3 are latently symmetric, and network B, where 6 and 10 are latently symmetric. If we just connect those two networks at the latently symmetric points with symmetric waveguides, so with equal waveguides or identical waveguides, whatever you call them, then the resulting larger system will have the latent symmetries on both pairs. So at those 2 points here and at those. So this is, I know that this term has been overused, but it's really like a Lego principle. So you can now stack more and more setups on top of each other, and you can build very large acoustic waveguide networks which have this pointwise parity property. Now, in case you wonder, well, I showed you only the simple stuff, but of course you can play the same game. So you can use this Norton automorphism, yes, so this Nautile suit from graph theory, design a large number of graphs, compute the corresponding Hamiltonian for them, yeah, by first checking, building the topological matrix, computing this diagonal B matrix, computing the Hamiltonian, and then check for latent symmetries. And if you do this on a large scale, and let's say play with a nice environment where all waveguide widths are the same, you can derive a large number of networks, and I have chosen my 5 favorite ones here. So you have the ice cone, you have the one-legged dancer and without head, you have the bridge, and I don't have names for those, but I just found them interesting to look at. And all of these networks have latent symmetry or let's say pointwise parity at the 2 wet marked points. Now, 2 last points for acoustics. Interestingly, so before we worked in the approximation where all the waveguides are narrow, so rather long, the widths are small. So it's a pure, let's say, waveguide network. And what is funny now is that you can use this Lego principle, which I showed before. So we to connect a cavity on it. Yeah. So before below we have waveguide networks, very small ones, and then we can connect larger extended networks onto it, which in this case have a symmetry. So if you look just at this coupled cavity here, first of all, it's rather big compared to the waveguides, and it can be even larger. But the important point is that it has reflection symmetry. So if you would now take this, just this coupled cavity, reflection symmetric, the eigenmodes naturally want, in quotation marks, they want to have parity with respect to this reflection symmetry. And now the usual game is if you couple this reflection symmetric cavity to some other subsystem, well, usually if this subsystem below is asymmetric, it has no reflection symmetry, the resulting eigenmodes of the total system will no longer be parity symmetric in your cavity, because the resulting system has no symmetry anymore. But now, what you can do is, if you have a latently symmetric setup with pointwise parity, and you connect this large cavity with small waveguides, which are, as you can see here, still plane waves, so they are one-dimensional waveguides. Well, what happens? You connect your cavity. The cavity wants to have parity symmetric eigenmodes. It is connected to an asymmetric subsystem, so this waveguide network here, but it doesn't see this asymmetry. All it sees is that the eigenmodes of this network below have pointwise parity. Yeah, and since everything is 1D here, I mean in the waveguides, it doesn't see anything which is the asymmetry behind is not seen, so to say, by this cavity here. And at the end, what we will get is that we have pointwise parity here and there, of course, and in our cavity here we have domain-wise parity, which is, well, there are so many small deviations, but as you can see, this is an eigenmode of the total setup, and we still have parity symmetry above here, although the total system is not reflection symmetric. Here on the right hand side is again shown the deviation of the, so R is the parity if you compare this point and this point for the first 10 eigenmodes, and you can see here if you make the waveguides larger and larger, so deviate from this perfect limit of narrow waveguides, well, the deviations, they are now a little stronger than before, but they are still comparatively low. And now, so you have the case, just to summarize, we have an asymmetric setup. We could evaluate the eigenmodes. We would see that they have domain-wise parity, but we couldn't explain. But if we go once again to this discretized picture, evaluate the matrix powers, or equivalently the isospectral reduction, we would find the reason for this rather unexpected behavior. Now, there's one more application, and then I think I will soon come towards the end of my talk. So before I have talked about eigenmodes, we could just as well go to a scattering picture. So this is our waveguide network here. It's one of the top 5, which I showed you before. We have latent symmetry for all eigenmodes, so parity for all eigenmodes on these 2 points U and V, which are marked in red. And then what we can do is, if we change the boundary conditions by opening this system at those 2 points U and V, we go to scattering. In the monomode approximation, we have, well, it's still a single mode regime. So it's a 2x2 S matrix because we have a 2-port scattering setup. And now normally what you would expect is that this scattering matrix, since the setup is asymmetric, would have not the same reflections. So the reflection of the first port should not be equal to the second, up to maybe some specific frequencies. But what you can find here is, due to latent symmetry of the eigenmodes of the closed system, can be easily shown that you have broadband equireflectionality, as we call it, between the 2 ports. Yeah, and as long as you are in the monomode regime, so as long as the frequency is low enough, this structure here, so R1 will be equal to R2 for all frequencies. And just to show you here why I'm so obsessed by latent symmetries, is that sometimes, not always, but sometimes you can understand them as a specific kind of symmetry breaking. So what you see here is a reflection symmetric setup where you would have R1 equal R2. So here is well, the reflection of the first port and the second, the absolute value and the argument. And then you can see they perfectly match. There's no blue curves visible here because we have a reflection symmetry. Yeah? These 2 ports are open. Now, if we break this symmetry by, let's say, just randomly taking out one of those guys, we come to an asymmetric system shown here. And then it's just as we would expect or guess at first glance. Due to this asymmetry, R1 is no longer equal to R2. However, if we now still break this symmetry, but instead of removing this waveguide here, just flipping it to the left, as shown here, we break the symmetry still, but we keep latent symmetry, and we have R1 equal R2. And the take-home message here would be, well, sometimes our naive guess that if you break a symmetry, everything breaks down, it doesn't have to be true. Yeah? Sometimes you can break the normal symmetry, but keep the underlying latent symmetry. And this for me is very interesting because I really like thinking in viewpoints. And for me, this is a viewpoint change. Instead of thinking about pure symmetry, of broadening the viewpoint to including also hidden or latent symmetries. Now I have, I think, 5 or 10 more minutes, Bryn.
In principle 5, but it's not a problem if you go for 10.
Okay, well, let's say make it 5. Okay, so in this very last part, I want to briefly talk about some generalizations of the theory. So before, what did we have? I always talked about latent reflection symmetries. So we did the isospectral reduction or effective Hamiltonian, whatever you want to call it, over two sides. And then we said, well, if this isospectral reduction is B-symmetric or reflection symmetric, then we have parity in the eigenmodes and so on. Well, of course, the concept of latent symmetries can be defined in a much more general way. And just to be strictly, give you a strictly mathematical definition, what I would say is the latent symmetry is that if you do your isospectral reduction over a set of S of sides, it could be 2, 3, or whatever number you give. If this guy commutes with a matrix M describing your symmetry for any value of this spectral parameter E, taking away, of course, those particular points where the inverse of this isospectral reduction is not defined. If this commutes here for all values of E, then your Hamiltonian is latently M symmetric on this set of sides S. And before, we had the special case of S equal set of two sides, U and V, and M was a reflection symmetry. Yeah, just this M permute the two sides. And then if you think about it and write down this commutator, what you will immediately get is that the isospectral reduction, in order to commute with M, has to have this structure. Yeah? It has to be B-symmetric, and this is exactly what we had before. But of course, the concept of latent symmetries can be much more general or broader. And now as a very last example, let's see, hopefully I need 4 minutes. Let's discuss some consequences of this. And in order to do this, well, let's look at this very simplistic, and you see I like Tor models, this three-side tight binding model. Well, it's described by this Hamiltonian, and as you can see, it's highly symmetric. Yeah, it is invariant under rotations and also reflections. And well, if you then go to group theory and check what is the group formed by these operations or these symmetries, you find that it is non-abelian. And we all know non-abelian groups lead to degeneracies in the eigenvalue spectrum of the underlying operator. And as you can see here, this is also, of course, what happens because the eigenvalues here, it's V minus H occurs twice. So our graph has a degeneracy. And this is common knowledge. Yeah? If you have something which is highly symmetric in the sense of non-abelian symmetry group, we know that there will be degeneracies. On the other hand, if we have degeneracies and there are no symmetries, we usually call them accidental, yeah? Simply because we don't know where these degeneracies should come from. And now let's challenge this a little bit. What you can see here is I went a little crazy. I designed this graph here, this Hamiltonian. It looks, well, it has this long range couplings, but apart from this, first of all, it looks funny, and second, it has degeneracies in the eigenvalue spectrum. But it's carefully designed such as to have no geometrical symmetry. Yeah, there's no invariance under rotations, reflections, and inversions or combinations. So are these degeneracies accidental, or is there something more behind? And well, there's two things. First of all, if you say, well, this guy is crazy, it's not so physical. There was the very nice point made by our referee in this paper. because we started with, initially in the first revision, we started with something like this, and then the referee insisted of putting something more physically feasible, and then we thought about, oh yes, we could start from a lattice with a unit cell like this, and then if you go to the Bloch Hamiltonian, let's say evaluated at the crystal momentum k equals 0, the connections between different unit cells, they become these long-range couplings here. Yes, so you can get from something very nice to something very ugly. Now, due to this, well, this is the Bloch Hamiltonian at k equals 0, so at the gamma point. And if you look here now, this is exactly where you have these degeneracies here and there. Same question. There's no visible symmetry. How can we explain it? And now the answer is, well, of course we designed this guy, but let's let's assume that you can do this also for other systems. So here in this case, if you do the isospectral reduction now over 3, not 2, but 3 sites, 7, 8, and 9, which are marked in red, then you get these guys. It's energy-dependent couplings, but apart from the exact structure of these A and B couplings, what is important is that it's highly symmetric. It's exactly this triangular structure, which is invariant under rotations and reflections, which we have seen before. Now, since this guy has a non-abelian symmetry group, it will have degeneracies. And we have made this, we checked all of this. So this connection between non-abelian symmetry group and degeneracies can be made also for nonlinear eigenvalue problems, such as we have for the isospectral reduction. Then since this is isospectral reduction, the eigenvalues of this guy will exactly be the eigenvalues of this, which again are correspond to the eigenvalues, so the band structures, so the values at k equals 0. And with this, we have explained these accidental degeneracies, so accidental level crossings here, through non-abelian latent symmetries. Yes, and now let me summarize. So what we have seen that latent symmetries are based on a symmetry analysis of the effective Hamiltonian. I know I talked a lot, and I talked about many different things, but for me, what is important is that the take-home message is that you can really apply this concept to a wide range of physical systems. All you need is this matrix eigenvalue problem, and personally, I think it gives you a new perspective on these systems. And a big plus, this connection to spectral graph theory is also a nice playground for interdisciplinary work. And well, it's always nice to learn something new, right? As an outlook, what could you expect next? Well, we are preparing a couple of experiments. We are also currently working on the generalization of this concept to purely continuous systems without having to discretize them first. We're also working on better methods for the design of latently symmetric setups. And of course, we're always playing, or at least I love playing with matrix powers. And there's always something new to be found. Yes, and then I would like to thank you.
Wonderful, thank you, Malte. That was a really nice, clear introduction to this really fascinating topic. So thank you so much for that.
Thank you.
We have time for questions. So now it's over to you guys in the audience. If you have any questions for Malte, then I'm sure he'll be happy to answer them. Yes, I see a hand raised. Whose hand is it? Yes, go ahead, Noah.